I'm originally from Portugal. I'm currently the director for the Leica Avia group. We develop software that uses artificial intelligence for image analysis in the space of microscopy. Over the last 15 years or so, I've been involved with other products that people might know. Imaris is the main one. And before that, I did my PhD in tumor angiogenesis and cancer biology. I'm originally from Portugal. I do like soccer, football, and surfing. I guess my pet peeve at work is when a partner or a customer asks me, how much training data will we need to get high accuracy? It's one of those questions that I still cannot answer. If any of the panelists can help me with that, I would love it.
Okay, I guess we will come back to that then, and hopefully we have an answer for you. Right, so let's move on. Maybe Rob Holt, if you want to introduce yourself next.
Sure, thank you, Kathy. I'm Rob Holt. I'm the manager for biological sciences at MathWorks, the people who make MATLAB and Simulink. And what I do there is I help support users and use cases in the life sciences. So I'm always out there talking to scientists and researchers about what they're working on, figuring out both how I can help them and how I can make the software better to help them. My background, I've been using open software for AI, for bioimage analysis for a very long time, all the way back to my graduate work where I was working on kind of the physics of medical imaging. And I used to work on medical image analysis, sort of algorithm development in the pharmaceutical services sector. So my biggest pet peeve when it comes to AI and general image analysis, not to be too much of a spoil sport, but it's when people are a little bit too gung-ho about using AI in the first place. Sometimes there's a perfectly acceptable classical solution. And in my experience, if you can use a classical solution, it tends to be a little bit more robust. So Luciano, perhaps we can compare notes on this front.
Okay, fabulous. So then let's move on to our next panelist, which is the other Rob Brisk, working for NVIDIA. If you want to introduce yourself briefly.
Sure, thanks, Kathy. Yeah, so my name's Rob. I spent the first 10 years of my career as a clinical doctor, working in the NHS in the UK. I specialize in cardiology. I was kind of a closet nerd for quite a long time, and then I came out into the world of computer science officially a few years ago. Spent some time doing some software engineering, and then got into a PhD program. I'm ashamed to say I haven't yet submitted my thesis because I got recruited by NVIDIA and life got very, very busy. But my job at NVIDIA is the developer relations manager for healthcare. So my job is to interact with the community, understand the ecosystem, and make sure that the NVIDIA platform is supporting what people want to do with AI across health and life sciences. So I work with people doing bioimaging work. My own research has been in macroscopic imaging, radiology primarily, but we also do NLP and a load of other complementary fields. My pet peeve personally is, I kind of agree with what Rob and Luciano have said, but my pet peeve is how quickly the research is evolving, the R&D is going, and the innovation is happening, and how slowly any of that benefit is getting to patients, because that's why I came into this field in the first place. Yeah, so that's me.
Okay, fabulous. Thank you very much. I've noted that down, so I guess we can discuss that later. And then the last person on the panel is Björn. He's one of our own and works for ELIXIR and the University of Freiburg. So Björn, do you want to introduce yourself as well, please?
Yeah, thanks, Kathy. Yeah, my name is Björn Grüning. I'm working for the University of Freiburg and heavily involved in ELIXIR as a tools platform co-lead. I'm involved in the Galaxy community, and what motivates me since years or a decade now is open source and accessible tools and infrastructures for our research community. And in that spirit, yeah, we are involved in different scientific fields. So not only imaging, yeah, but recently also imaging, AI, machine learning. And I completely agree with Rob that not everything that can be solved with AI should be solved with AI probably. But my focus here is probably in this discussion also to discuss a little bit the open source aspect and the definition and how we can make the infrastructure that we have more accessible to researchers. And with that, maybe help what Rob actually pointing out, that it's very hard to get that to a patient. And a key solution for me is really enhancing accessibility.
Fabulous, thank you very much. So we've got a great panel. And so I thought we're just going to have a look again at what the audience has submitted through their Menti when we ask them with what kind of images they work. And I hope you can see my screen. So a lot of them say they work with images of tissues, cells, organoids, cell lines, bacteria, skin. So I guess this is kind of the answer we would expect in the life sciences anyway. So Luciano, I think I'm going to pick on you first, since you work for Leica, who are a big producer of microscopes, and you recently joined them from they acquired a software company, S-Vision, I guess. And I think I pronounce it correctly, Avia. And so I guess there is an interest of combining the more hardware side with the software side. Is that something that you see across the sector? Are these companies that are produce the hardware, the microscopes, now moving into the software as well, in the data analysis side of things? And yeah, is that something you see overall, and why are they doing this?
Yeah, I'm extremely biased there, of course, because I'm myself, even from my research time, the biggest interest of mine was really in creating insights from those images. Even though, like every PhD student, I also spent years in a dark room acquiring data. And that is a trend. Certainly, the microscopes, the hardware has become much more capable in the last decade, able to capture much larger images at higher resolution over longer periods of time. And that creates a bottleneck that we're all familiar with. There's a lot of data accumulating on Amazon's and Google's servers and local servers that then need to be processed. And so having good image processing engines is essential. And that's where a lot of us come in. Certainly at Leica, there is a huge focus on creating good insights from the high quality images that are being generated. And I think that's a trend across the whole community, not just commercially, but the whole life science community. So that's certainly a trend.
Mm-hmm, mm-hmm. So combining everything under one roof. I guess Rob Holt, I'm gonna come to you next, because you are working for a company that produces software that helps scientists to make sense of the images they generate. And of course, as a company, you want to make money and profit, but as you've stated in your introduction, you're very interested in open software solutions as well. So why is that important in this sector, in this specific segment of life sciences, and why are you interested in that as a company?
That's a great question. And from a philosophical standpoint, what we want to do is make sure that people have the best tools for the job. Hopefully, that's the software that comes from the company, but even if it's not, we still want to make life easier for scientists and researchers who are out there solving problems, making life better for society writ large. And it's important for us to make sure that solving problems for them, they're access to compute, their access to algorithms, and their ability to solve problems is as straightforward and as easy as possible. And to do that, there are so many people who are out there developing good tools, developing great tools. There's no reason for anybody to redevelop the same thing over and over again. And so from a company standpoint, that's why what we're doing is what we've done is we've had software that interfaces with other software. So you can call Python from MATLAB and MATLAB from Python, and we have interfaces with R. But even more than that, there are a lot of people who are making really good wrappers. But when it comes to open software enablement, another thing that we've seen that's becoming very popular and also helps to add to the robustness of software is containerization. And so right there, what you have is something, almost a package that you can pick up and move from place to place that other people can run very straightforwardly. So it's important for us as a company to support open science because that's what makes life easier for people. It's also how a lot of science is being done. And what we want to do is continue to support the people who are solving those problems.
Fabulous. I'm bringing in Björn here because you're coming from the academic side. So I guess if you could ask anything from a company like MathWorks, what would that be? What would be the main thing you would want them to do to make the life of academics easier?
Open sourcing everything, or at least MATLAB. No, I mean, honestly, I think it's interesting what Rob is saying, and I think we all agree on that aim, right? That we want to make it easier for the user. But the question is actually, who is the user, right? If we just think the scientist is the user that codes in MATLAB, that's one thing. And yes, it should be easy. But there are a lot of other people involved to actually spin up large infrastructures. And I can just tell you from my experience and from our university, it's a huge effort. And I discussed that actually with the other Rob as well. I think what companies shouldn't underestimate is that administrators and infrastructure maintainers do need to maintain these infrastructures. They need to install the NVIDIA driver. They need to set up an MATLAB server, a licensing server, and so on. And this is all additional overhead that the university also needs to pay, right? And in some sense, these are also users. And one other aspect is that in the university field, I mean, we can buy hardware. So we can get money for hardware, but we can hardly get money for persons. But these persons are needed to maintain proprietary stuff because we cannot use our open source tool chain to deploy entire clusters, right? We always need to have a special quirk to install MATLAB, to install NVIDIA. So all these proprietary stuff, we cannot treat with our usual open source treatments. Mm-hmm. And this is money that ends up on the person month stack, not on the hardware stack, not on the license stack. Mm-hmm. And I would like that companies recognize that it's not about the license per se. It's also not about the philosophical aspect. It's in the end, it's also a money aspect of I need to hire an extra administrator to maintain whatever an NVIDIA cluster in contrast to open source, mm-hmm. whatever deployments.
Mm-hmm. Well, then let's bring Rob Brisk in to the discussion because he works for NVIDIA. I guess everyone knows what NVIDIA does. They design graphic processing units. And in the past, the company didn't always see eye to eye with the open source community, Rob, if I'm not mistaken. So, and what Björn has just brought up, the kind of target user is maybe not necessarily the user you would usually expect. So do you want to comment on that?
Yeah. Sorry, just got a cough. Yeah. I think Bjorn makes some great points about some of the challenges that we're facing at the moment, and as he said, it's something we've discussed before, and really great to get this kind of feedback. I think the whole ecosystem at the moment is at a challenging time because we're seeing a big shift in the way people work. So the traditional HPC clusters are not always suitable for what we're trying to do with AI. And as Rob H has pointed out, there's a big shift towards containerization that comes with some significant challenges. And people are wanting to use more specialist hardware, like NVIDIA GPUs, to accelerate these very high intensity workflows that are becoming very popular. So it is, you know, for a small IT system in a university, say, if they want to actually make a switch from something like Slurm to run like a, you know, an orchestration and load balancing platform like Kubernetes, so that people can access a cluster and interact in real time to develop their code with specialist hardware, that's a challenge. It's something that in NVIDIA we're very aware of, and there are big moves to address this. So over the next year, 2 years, you're going to see a lot of stuff happening from our end to try and really make this a lot easier for the systems administrators. And actually, the feedback that Bjorn gave us last time we spoke, I took straight up to our CEO, Jensen Huang, who leads NVIDIA, and we had that conversation. So at the very senior most levels, we really care about the user experience. I think it's a wider challenge for the wider community, and I think it's not one that's going to be just solved by us, NVIDIA, and other hardware providers alone. I think it is just the case that technology is becoming leaned on more heavily. People are expecting more from their clusters, and we're going to have to find slightly new ways of working. To what you said before, Kathy, about the open source community, I mean, I've been in NVIDIA 9 months, so I can't really comment on what went before that, but certainly at this point in time, now there are bits of the NVIDIA tool chain that are not open source, and you know, there are reasons that some software packages get open sourced and some packages don't. You know, it's much like I work a lot with Big Pharma. It's a similar thing, right? It costs a lot of money to develop very high-end stuff, you know, medications and hardware that changes the world, and that's got to come from somewhere. I would say these days NVIDIA is very focused on the open source community. We back a lot of big open source projects. In fact, I'm going to talk about them in the second half of this session. Yeah. And I'll also talk about the fact that we're trying to make containerized applications friendly to the open source community as well. So we'll come to a bit of that stuff later.
Yeah. I think we're changing gear a little bit now, and to have a look at one of the questions that we asked the audience. We asked them if they are proficient in using machine learning and AI to analyze imaging data, if they are currently learning to do this, or if they're really struggling. And it seems that people are either in the learning stage or in the struggling stage. So maybe Luciano, for a company like Leica that really covers the kind of software aspect and the hardware aspect, and of course wants users to make use of the whole pipeline, how do you go about this? Because we see probably a big discrepancy at the moment where users might not be able to actually use what you're providing because they don't have the necessary training. So do you see there's a gap, and what are you doing to kind of bridge that gap?
Yeah, this is the same as with every new technology. And I would echo what I think it was Rob Holt mentioned, not everything requires AI, but since the focus of this particular panel is about AI, I keep focused on this. So it is a new technology, especially for the life science microscopy field. The last 4 years have been tremendous in terms of new developments, both open source and not. It's inspiring to see what has happened actually in the last 4 years. The number of publications is skyrocketing. Number of applications is also skyrocketing, but still the large group of users, potential users, are not really familiar with what AI is at the essence. They see some results, a lot of marketing, not just from companies, but generally there's a lot of communications about about the power of AI for this and that and the other. It seems like it will solve everything, but it is lagging. The true understanding of the power of this kind of technology is lagging. And I think we're still very much focused on very narrow applications. Applying a UNet to do image segmentation is still what a lot of people do, or restoration. I think the future is much more about integrating chains of steps that may include, probably will include, some part that is an AI element in a smarter way to do image processing, in a smarter way to interact with your software. So that's my focus. That's what we're looking for, is try to move towards automation of the processes using AI, rather than very narrow applications where we detect some cells. I mean, that's important, of course, but it's in the integration that the value comes.
And I guess a lot of that is related to what Rob Brisk mentioned earlier, the slow benefits to patients, either human or animal patients, I guess. So we don't really see that is translated into real life yet. So maybe, I don't know if either of the other panelists wants to actually comment on that. Well, when will we actually see those benefits, and how are we going about training people adequately? Yeah, maybe Rob Holt, you've unmuted, so I go with you first.
Rob, I'm sorry, I didn't mean to cut you off there. So I think that's a really great, I think it's a really great point. And we're seeing just such amazing shifts in the capability of AI in a relatively short amount of time. It wasn't that long ago that it was borderline impossible for a computer to tell the difference between a picture of a cat and a dog. And now that's something that we assign as a homework problem for undergrads or even high schoolers. So what we're seeing is huge advancements just constantly that are absolutely amazing. And as Luciano said, it can be hard to keep up, but I think what we're seeing is that these tools are continuing to grow. They're continuing to become more abstract. And that level of abstraction is actually opening up the ability for everyone to use these tools. That is, it used to be you had to know, base computer code to write your own neural network, but now there are higher level packages and higher level languages that allow even people with a modicum of training to really do complicated problems. I often compare it to HTML for people who aren't so familiar with the AI space. It used to be that you could get a job for $90,000 on Wall Street making just programming basic HTML in the 90s when everybody needed a website. But now it's something you can make the summer intern do. So we're seeing everybody move in that direction with AI. At the same time, I think that the AI tools are becoming so sophisticated that we're also, that now what's happening on the bleeding edge is starting to look a little different. And one of the things that's really fascinating me is the hybridization of a bunch of different data types. So it's not just semantic segmentation for image analysis anymore. It's images and genetic data and doctors' written text to analyze the prediction of a treatment outcome. And I think that's just absolutely fascinating for the future. So I think when I think it can be hard to find all of these things accessible, which is why I really love to see when everybody is working on integrating this in the classroom to get people started learning younger. And I also love to see I'd love to see how much excellent training material there is on the internet, whether it's somebody doing a high-level review on YouTube, whether it's a panel discussion to elucidate some of the finer points, or whether it is somebody making a new course about some of these new methods. Really just a fascinating time to be part of the experience.
I see that Luciano raised his hand, so you probably have a direct comment for Rob.
Yeah, it's a comment and a question. It's very short. So it goes, I kind of see it going in two directions. On the one hand, people want to know what the technology is and understand it. On the other hand, people also want to use abstractions so that they can get down to business. Now, they apparently go in completely opposite directions. And regardless of what environment you're developing, open source or not, that is a problem. So I'm wondering how the other panelists here see that, and how can that be addressed? So provide trust by showing everything, and also provide abstraction so that you can get down to business.
Okay, Rob Brisk, you've unmuted first, so there you go.
I think that's a great point that Luciano makes, and I think Rob made some great points as well. There's some caution to be exercised here, right? Because as these tools become more abstract and more accessible, are we foregoing some basic training that you really should have before you start messing with AI models, particularly in high stakes field? I mean, bioimaging generally feeds into either preclinical research, which will ultimately lead to the development of therapeutics, or directly into the clinical setting. We don't really want people who don't understand the nuances of working with neural networks. I mean, first thing that I can't remember if it was Rob or Luciano made the point, we don't want people using AI when you don't need to use AI, right? But when they are using AI, I mean, you've got to understand, the danger of bias, what happens with covariate shift. And that's hard, right? I mean, I spent a long time training for clinical medicine. I mean, I started med school in 2004, and they didn't let me stick a wire in someone's heart till 12 years later. That's kind of, that stuff was almost easy compared to getting to grips with, getting to the point where you can articulate how a transformer-based neural network works. I mean, this is hard stuff. Yeah. To me, there need to be good resources for people who are interested to get upskilled. There need to be good resources at the concept level for people who want to demystify but don't want to do. But above all, there needs to be great communication between the people who have expertise in different domains, because that's when it all comes together. When you get a team with clinicians, subject matter experts, and data scientists, and computer scientists, people like Bjorn, who do this fantastic job of managing the infrastructure, that's when you see the magic happen, I think.
And I'm glad Bjorn raised his hand, because I wanted to bring him in anyway. I guess because you sit in an academic organization, training is your bread and butter. So yeah, you're closest to the student. What do you have to respond to?
Yeah, maybe at first the response to the direct question. I think what we are seeing is kind of normal, right? So we have always these technology breakthroughs, like with the first generation of sequencers and so on. And as all of us already mentioned, at first it was hard. There was only a few people that were able to analyze these data sets. And nowadays it's a click on a button and you get genomic data analyzed and so on. So to some degree, I think that's normal. And this is a normal procedure in our community. So we just need to make it accessible, and we need to write documentation for that, and good documentation. But we also need to go out and actually teach that to the students. So, and I mean, as ELIXIR, I would just like to point out there's an entire training platform in ELIXIR that is dedicated to I mean, in non-COVID times, to really talk to the scientists, to educate our scientists in all various kinds of scientific domains. So I would like to, I mean, what we don't have so much is actually that we are working with companies together to train scientists. So I would love to have if people buying microscopes, that companies are giving training on the microscope, but looping in let's say the academic, the open source world, and then you give a training on data analysis and so on. But I think, and I like the comparison of Rob Holt. I mean, the web is a very nice example, but the web was built from the ground up on open technologies, right? And this is maybe the key difference here. If everything is open, if everyone can access it, everyone could potentially write training material for that. And we need to come to this point. And I mean, I can just say from my perspective, in genomics, more or less all tools are open. We can have a lot of documentation. But the more you go actually to the hardware vendor, when we have proprietary formats, when we have proprietary software in metabolomics, in proteomics, and so on, the less documentation you have, the less community growth you have. And maybe that's a relation, maybe not, I don't know. It's just my suspicion. So I think my key points is ELIXIR has the infrastructure. ELIXIR has a training platform. ELIXIR has a tools platform. I think both Rob mentioned containers, right? We are supporting a huge project called biocontainers. So we would love to work with you, at least on the open source parts of things, and make use of us, make use of our community, because we obviously are also interested to reach your customers, to train them.
Fabulous. Well, what I hear is open source advances science faster, and that's, I guess, what we all want. Well, hopefully you guys will follow up after this and put something nice together. So I just wanted to come back to what Luciana said at the beginning. How much training data do you need, and where do you get that you know, high quality standardized training data from? Does anyone on the panel have actually an answer for him, and so he can sleep sound tonight?
How much training data do you need? How much do you have?
It's a big problem.
Yeah. We take all.
I mean, there is a simple answer, but so maybe you know, I'm not perhaps as expert in this field as others on this particular panel, but in my experience, you know, you can have some back of the envelope sort of benchmarks for roughly how much training data you need. You know, a few dozen to a few hundred for machine learning, a few hundred to a few thousand for deep learning. But even where you draw the line in between those two things isn't like super well defined. But broadly speaking, what somebody needs is a representative data set that encompasses the entirety of the expected range of features of whatever they're looking for. And sure, you can augment it, but you can only do so much there. Really, what you need is representative data. If the right amount of data is the full representation of the space that you're trying to traverse, right?
The interesting thing in the bioimaging domain is that comprises all the different permutations you find within a population of 6 billion humans, plus the animal kingdom. That's kind of hard, right? Yeah.
Not a satisfying answer for Luke.
Sorry.
No, that I don't know if that there's ever going to be a definitive answer to that, because the problems are so varied, even within a very narrow application of let's detect these cells. You know, the cells could be labeled in so many different ways. Yeah. They could occupy a large amount of the data set or a small amount of the data set. There's so many variables. We find that it's, yeah, I agree with Rob Holt about, you know, hundreds, less than hundreds for machine learning, and for deep learning, thousands would be good. But we've also seen quite a few cases where dozens is okay for deep learning, as long as you have enough of the distribution captured. But it's very difficult actually to get to that number. One thing I wanted to ask everybody about unsupervised learning, actually, unsupervised learning approaches. Oh, my dog is in the room. Didn't realize that. Sorry about that. My question was, if you feel like unsupervised learning methods are appropriate for biology and for, you know, research in the life science space.
I guess we'll give that to Björn, if you want to answer that, and then we will have to cut the panel discussion off, I'm afraid. So Björn, I give you the last word.
Oh shit. I fear I cannot answer that completely, because this really depends on the domain where you are in, right? I mean, if we talk about life science, that's too much of a broad scope. There are use cases, I think, where unsupervised real learning is useful, where you can use it, but of course not to everything. So I don't think I have a good answer to that. Sorry.
If anyone, Rob, any of the Robs have a good answer.
Yeah, I'd kind of, I know we're running out of time. I'd ask for that to be qualified a little bit with what do we mean by unsupervised learning? I mean, if we're talking about techniques like, clustering, then actually, there are situations where that can be very useful for coming up with, more nuanced phenotypes of certain conditions or disease states. So, I mean, if we're talking about unsupervised learning in the sense of like a generalized artificial intelligence that just gets on with its work without human supervision, I don't think we're quite there yet, but it'll be an interesting bridge to cross when we get to it.
Fabulous. Well, we have to move on with the program. So thank you very much to the panelists. And I would ask the panelists if they could pop their email address into the chat box. So anyone who wants to follow up with you could do that easily if you're happy with that. And then I'll hand over to Rob and his colleagues who have prepared a little demonstration for us. So thanks again to Rob, Björn and Luciano for making the same time today. And yeah, Rob, please take it away from here.
Okay, brilliant. Thanks, Kathy. And thanks guys for a great discussion. So, Kathy, just before you disappear, we've got till 5:30, is that right?
You've got till 5, yeah, 5-ish, so 45 minutes.
Oh, 45 minutes, okay, so quite a short one. Okay, fine. In that case, what I'm gonna do, we're gonna split this session into 2 parts, and we'll cram in as much as we possibly can. I've got a bit to show, and then I've got a colleague, Johnny Hancock's on the call, who's got a couple of open source tools to show as well. And we've also got our colleague, Benedict, manning the chat. Benedict is one of our data center experts. So if you've got any questions about running GPU clusters or working with common scheduling and orchestration platforms, then please do make full use of the chat to kind of pick our brains at the moment. What I'm going to do during my part of the session is I'm going to introduce a great open source GPU accelerated medical imaging framework called MONAI. While I talk about MONAI for a few minutes, I would love for people, let me share my screen here. I'd love for people to answer a question for me in the chat to decide what we do with the latter part of the presentation. This is the question, are you comfortable with the basics of developing with containers? Just a simple yes or no answer dropped into the chat will let us know how we want to run the rest of this session. If the answer is generally yes, then we'll drop out that bit and we'll spend a little bit more time talking about the open source frameworks that are worth knowing about. If the answer is generally no, that people aren't comfortable with the basics of developing with containers, then I will endeavor to do a very quick 101 run through of how you can get started developing Python-based AI applications in a container-friendly environment. So please do use the chat to answer that question while I talk, but let me now move on to talking about MONAI. So let me start with a problem statement, because I always think that's helpful for focusing minds. So let's say, I'm a cardiologist by training. Let's say that I want to develop a deep learning algorithm to segment out the left ventricular cavity from MRI scans of the heart, which is a common burdensome task we do in clinical practice. And it's been well explored in the world of artificial intelligence. It's basically a segmentation task. So I want to use this as my opportunity to dive into deep learning a little deeper and create an application based around that framework. Why am I going to reach for MONAI, which stands for the Medical Open Network for AI? I'm actually showing you the homepage, but if I flick over here, it's got a nice live graphic. So I'll show you the actual homepage because it's prettier. Well, let me explain what MONAI is. MONAI is both a community and a framework. So as a framework, MONAI is mostly now pitched at the macroscopic medical imaging space, i.e. it's designed for working with radiology volumes like CTs, MRIs, X-rays, ultrasound, and so on and so forth. Though I will come to this in a moment, it is rapidly expanding. MONAI is built on top of PyTorch, which is emerging as the leading deep learning framework. And PyTorch runs on top of Python. And that's what we see most data scientists in this space using at the moment. MONAI started out as a collaboration between, well, a lot of the background work was done by King's College London, and then King's College London got together with us at NVIDIA and said, listen, what we want is a standardized framework that people can really gather around in this community. It'll be high quality, it'll address all the things that people want, and it'll be performant. Because at the time that this was conceived, that didn't really exist in the radiology AI space. Now, this quickly gained momentum, and if I scroll down the webpage here, you can see some of the partners who are currently involved. So you'll recognize these names as global leaders from both academia and industry. MONAI is rapidly gaining gravity, so more and more people are joining. And it's brilliant because we have people who are very active in the bioimaging research space who know what that community needs and can start writing the code. And then we've got people like NVIDIA involved, where our engineers invest a lot of time in optimizing this framework. Let me flick over to a PowerPoint presentation just to run through some of the key functionality in MONAI that I like. I'm just going to scrape the tip of the iceberg here. There's lots to explore in MONAI, but let me tell you some of the reasons I like using MONAI. MONAI has a user-friendly API for anyone who's already a PyTorch user. If you're not a PyTorch user and you're interested in deep learning, then I would encourage you to go check out PyTorch, because it really, a couple of years ago, there were loads of deep learning frameworks around. Now there are just a couple that are kind of really got traction and are well supported. PyTorch does seem to be emerging as a leader. Here you can see you've got a whole bunch of MONAI transforms that are off-the-shelf things you can do with your images during the process where you want to load up your images, do some manipulation and augmentation before you run a deep learning algorithm. So the transforms off the shelf in MONAI include a Nifty loader. So Nifty is the format we generally use when we're working with volumetric studies in a data science environment. You can do image augmentation that applies to both 2D and 3D images, which is really nice because you won't find that many good 3D augmentation libraries out there. And you can also push your NumPy tensor. So you usually do image augmentation on the fly on a CPU, and then you can push that tensor over to the GPU as a PyTorch tensor with a single transform. And what you're seeing here is you wrap all your transforms in a nice compose module, just like you would do with Torch Vision. So it's an elegant and efficient way to code. You get a whole bunch of neural network architectures with MONAI you can invoke with a nice, easy API call. They're very customizable, but if you're a relative beginner and you don't want to do any customization, then they're super easy to use without going in and tweaking the variables. One of the things I particularly like is it's got a 3D UNet implementation here in MONAI. That can be a bit of a pain to implement if you're trying to do it yourself. Similarly, there are some loss functions that you commonly use in the bioimaging domain. So segmentation, we've heard mentioned a couple of times today already. So you've got a dice loss here where you can flick Shakard smoothing on and off. You can include or exclude the background pixels. This I've used a number of times and I really like it. And again, it's a well-optimized, efficient implementation. And the final thing I'm going to say, though, there is lots more to explore, and I'm going to end the introduction to MONAI by encouraging you to go and check out a couple of the repos and the tutorials. The final thing I'm going to say now is that there is a focus on reproducibility. So there is some nice functionality here for introducing determinism to your deep learning model training so that other people can reproduce and validate your work, which of course we care about a lot in the health and life sciences community, including of course bioimaging. And this isn't a feature that I'm going to talk about, but not only is MONAI great to use if you're working with radiology studies right now, but it is also rapidly expanding into other spaces. So I realize much of bioimaging is about microscopy analysis and even deeper down the technical chain, things like imaging mass cytometry. People are starting to apply AI to a lot, and label-free cell tracking and that kind of business. MONAI has a pathology working group that's already beginning to produce some pipelines and tools. And it's also expanding into the area of deploying AI as a service within a clinical setting and addressing all the unique needs that come out of that community. So as well as being a great framework to use now, it's definitely a space to watch as MONAI evolves. Let me just flick back up to this slide. If anyone wants to take a screenshot, I've got a link to the MONAI website and a link to a bootcamp repo that I'm going to show you now. A couple of other links for things I may or may not have time to talk about today. Let me flick back over to my web browser though. And so MONAI, I'm going to move my Zoom thing here. MONAI has the GitHub link from the homepage. And within the GitHub, you've got the standard MONAI tutorials, and you've also got a more detailed bootcamp here. I've got this open in a separate, oh no, I don't have this open in a separate tab, but I will have in a moment. So the MONAI bootcamp has 3 days worth of notebooks that gently take you through from the basic functionality to more advanced stuff. So this is where I would start. If you're gonna take the time to get hands-on with MONAI, and I would encourage you to, if you're working in this field, this is a great place to start. That's a real whistle-stop tour on MONAI for the purposes of time. Let me work out how I open the chat on Zoom. I was telling Kathy earlier, I've used Zoom surprisingly little because I use Teams mostly.
If you go to the control panel on the bottom.
Where's that? Is it?
Oh, if you're sharing, it might actually be on the top.
Oh, lovely. I've got it. Yeah, perfect. What I just wanted to do was actually check the chat. Can I do that from here?
Yeah,
okay, so lovely. It looks like we've got mostly yeses from. There are a couple of people who are saying no, they're not familiar with containers. Most people are saying yes, though. So that's good because that's kind of time consuming, and I can drop that bit and spend a bit more time talking about Johnny's side of the presentation. Bjorn's also asking about Onyx, PyTorch, and the distribution of models. I wonder if Johnny or Benedict could field that question in the chat. If not, Bjorn, I will answer that question once I've finished talking, because otherwise I'll lose my train of thought. The answer is yes. Yes, we do. I have worked with Onyx and converting PyTorch models to Onyx. It's not always a completely pain-free process if you're using sort of more customizable layers. But generally, there's great tooling available out there to convert your model to Onyx. And it's the default way of getting a PyTorch model into our Tensor RT, which is our open source optimized serving engine for models. We may or may not touch upon that later. Let me just check. Johnny Hancock, are you on the call yet?
I am on the call. Hopefully you can hear me.
I can. Johnny, I was going to do a tiny bit of just talking about some of the memory transfer stuff with CPUs to GPUs and just briefly show Insight systems, but we're a little bit tight on time with half an hour to go, and I don't know how much that overlaps with your part. I wonder if your notebooks would be the most valuable way to spend half an hour.
Why don't you I think the Insight stuff would be useful, and then just leave me, however long, 10 minutes or so.
Perfect. That's great.
I'll cover off.
So okay, I'm bypassing a load of stuff that I was going to cover about containers here. What I'm going to do is I'm going to sbatch this command here. Okay, great. And I should over here be able to just, yeah. Okay, what I've just done, and I've not explained at all how I've done it, is I'm speaking to you from a Lenovo ThinkPad laptop with no GPU running Windows 10. But on a remote workstation, I've just run. You saw me scheduling a container to run on top of Slurm, and inside that container, I'm running a Jupyter Lab server. So I've just remotely accessed this through my web browser now, just to familiarize you with where we're at. Okay, let me spend 5 to 10 minutes talking about some of the key factors you want to think about when you're trying to get maximum performance out of your GPU. And this is really particularly important when you get into microscopic imaging, where the image is a whole slide image at 40x resolution is a massive piece of data. And performance really matters when you're trying to get through a significant chunk of, say, TCGA and do some sort of analysis there. You really have to be as efficient as possible, or either your experiment isn't going to work, or your colleagues are going to hate you because you're going to dominate your shared compute resources. So I'm just going to run through a couple of basic pointers regarding data transfers between CPUs and GPUs, and that should segue quite nicely into what Johnny's about to talk about. Jupyter Lab, for anyone who hasn't used it, is a fully functional IDE, but this Python editor looks a bit crap. So I'm going to go to something prettier over here. I've got the same scripts open in Sublime Text with nice coloring. Okay, let me explain what's happening here. I've written a quick script to profile some code. I'm just comparing simple matrix multiplication running in NumPy on the GPU. So you can see that here. I've just created two 3-dimensional matrices populated with 1s, and I've multiplied them together. In this function below, I'm doing exactly the same thing, but I'm running this matrix multiplication on the GPU using PyTorch. And down here in my main thread of my script, this is a pretty typical sort of code profiling workflow for anyone who's interested in taking a deeper dive into the performance of their code. What I'm doing here is I'm warming up the system by running a few loops of the functions I want to test. So if there's any smart memory caching going on in the background, you let that happen during the warm-up so it doesn't skew your results. Then I'm going to time my function by using Python's built-in time module and the perf counter function here. I'm not going to use time.time. This is to do with syncing up with clock cycles. It gets a bit technical at this point, but this is the call you want to use if you're profiling code. Now, because I'm profiling GPU code, I just start my timer here. I'm going to run 1,000 loops of my matrix multiplication on the CPU, and I'm going to end here. And then I'm just going to print out the average time per loop. And that'll just tell me how my CPU is performing. I'm then going to do the same thing with PyTorch and the GPU. The one thing to watch out for here is when you're profiling GPU code, GPUs, so CUDA kernels will by default execute asynchronously. So first thing I want to do before I start profiling is use this call here, torch.cuda.synchronize. By the way, if ever you're trying to profile code in something like TensorFlow, which doesn't have quite such a neat call to synchronize your CUDA kernels, you can import torch and use the torch call. Okay, so what torch is just passing this call onto your GPU. It's not specific to PyTorch tensors that you have on the go. It will synchronize all your CUDA kernels. So this is a nice little functionality to use during code profiling. And down here, you'll see between every loop of my function, I'm going to synchronize my kernels. If I didn't do that, then the GPU wouldn't wait for one function to execute before it starts the last, and I'd get a falsely reassuring performance. So that's just a very quick intro to what I'm doing here. And now I'm going to introduce you, I'm going to just run the code and talk you through what's happening. And I'm going to introduce you to an even more detailed profiling tool that NVIDIA makes that looks a little bit frightening, but is actually really useful once you've got the hang of it. So first thing I'm going to do is just run the code. And there we go. So what you've seen here is that I'm getting a 2x speed up by running matrix multiplication on my GPU, right? Which to me doesn't seem right because GPUs are designed for matrix multiplication. It's where they excel. I should be getting at least an order of magnitude speed up from what I'm doing here. Anyone who's well used to working with GPUs will have already spotted why that is. But let's say I want to dig a little bit deeper into my code. Here's what I can do to do some more detailed profiling. There's an NVIDIA tool called Nsight Systems. I think I actually have it open on a tab here. You can download it from the website. It's not an open source tool, I should say, but it's great for developing open source code and it's completely free to download and use. So you can just go to the website and pull it. I've installed it once on my Windows 10 laptop that I'm speaking to you from so that I've got access to the GUI. And then I've actually gone and installed it inside my container so that I can actually profile my code within this containerized environment. So the command I'm going to run is nsys profile, and then I'm just going to go ahead and use the same command here to run my script. What will happen is that my script will run, and then once it's done running, it will dump a report with a .qdrep extension in my present working directory. You can see I've already been running this code earlier to make sure everything was working for today's demo. So I've already got a few qdrep files. This is, I'm going to switch over now and open the report generated by that script that I just showed you in the Nsight Systems GUI. Here is report 1. Let me shift my Zoom screen. I'm going to silence the error warnings here. Bit of a busy user interface here, okay? This is kind of an advanced profiling tool, but it's not as scary as it first looks. What I really care about right now, I want to know what my GPU is doing and why my GPU isn't way faster than my CPU. So I'm going to ignore all the noise up at the top here. I'm also going to ignore my dog barking in the background. I'm going to go straight down to this row here, which tells me what is happening on my CUDA-enabled hardware. You can see nothing's happening for most of this time frame because the matrix operations are executing on the GPU. This is where things start to get busy. Clearly, I can make out absolutely nothing at the moment, so I need to zoom in. So I just highlight this little section here, double click. Remember, we executed my code my function 1,000 times. So what you see is 1,000 clusters here. So I just want to zoom in on one single execution of my code. And here we are. Now, all I do is I hover my mouse over the activity bars here and I'll get a tooltip. So what I'm seeing is that each time my function executed, I get this much time, this little green bar's worth of time taken up with something called memcopy H2D. H is host, meaning my CPU memory. D is device, meaning my GPU. So this is the tensor I called X being transferred from my CPU to my GPU. This is the tensor I called Y being transferred from my CPU to my GPU. And if I go over this red bit here, this is the reverse. This is mem copy from the device to the host. So this is Z, which was the result of X times Y going back to my CPU. This tiny little smudge here, this is my CUDA kernel actually running. So the vast majority of my wall time here is just shifting data around. And this is almost always true, because you have to, when you want to send your data to your GPU, you're going through a PCI bus with limited bandwidth, and that tends to be your bottleneck. If you have a really high-end sort of server, what you'll find is you've got SXM4 slots, which has a higher bandwidth. So that's to increase performance. It's not just because we're bastards and we don't want you to use your consumer cards in a high-end server. There's actually a good performance reason for that, but there is still likely to be a bottleneck there. So if I go back and if it's possible to refactor my script so that what I do instead is, in my main thread here, I send my tensors over to the GPU once, and then I keep them there while I run my 1,000 loops of the code. If I can do that, it's likely I'll get better performance, right? So I've refactored my code to achieve that. I'm sending my tensors to the GPU. I'm doing 1,000 operations there, and I'm not doing any back and forth. Let me just flick back over to actually put my money where my mouth is. I'll clear the console here. So Python test2.py. And if we look at the time now, so now I have over an order of magnitude speed up in my code because I'm not messing about with memory transfers. And let's just flick back to Nsight and look at the report. Here's one I generated earlier. Now, if I scroll down to my CUDA device again and I zoom in, you can see I'm using much less time on the GPU now. And if I zoom in on this and I zoom in on this again, so for each one of these functions, I'm just running a tiny bit of CUDA execution. And so it's much more performant. And just a final bit of interest before I hand over to Johnny, I'll give him a nice, neat 20 minutes to talk. I've created a third script where I've actually put the torch synchronized function outside of the activity loop so that the CUDA kernels will only synchronize at the beginning and the end of the 1,000 functions, not after every function. So just to show you that actually that does make a fair difference to performance. Yeah, you can see I'm almost another order of magnitude faster because the CUDA kernels executed asynchronously. The one thing that will be an interesting lead-in to say for Johnny is that when you go back to my report here, where I'm sending tensor X and tensor Y to the GPU, notice that I'm doing this in 2 isolated packets because I haven't done anything clever with memory pinning. I'm not memory streaming. And so this is actually, I'm making my code even more efficient. Not only am I transferring my data back and forth between each function, but I'm streaming my memory as separate packets. Now, to talk about why this is important, particularly in the world of digital pathology, I'm going to hand over now to you, Johnny, if that's okay. And I will stop sharing my screen and let you share yours. That was the wrong button. Stop share, that would be the button, wouldn't it?
Okay, hopefully I am sharing now.
Yeah, looks good.
Great. Thanks, Rob. Yeah, so I'm just going to talk about a couple of different open source based projects and the sorts of things you can do with them, which I've been playing around with. So I should probably introduce myself, really, shouldn't I, first? So I'm Johnny Hancock. So I'm a solution architect. I work in the same team as Rob. And my sort of specialist area is probably pathology and a bit of radiology as well. So I spend a lot of time messing around with some of our technologies, hardware and software, and trying to help customers get the most out of their technology investments. So to that end, I wanted to show a couple of little experiments that I did using some of our kind of tooling, some of our open source tools. So like Rob, I'm running a Jupyter notebook here. So I've got a workstation underneath my desk, which has got a couple of GPUs in it. But I'm actually running all this from my laptop. So on my workstation, I have spun up a container. So that container is running, it's got PyTorch installed in it. And it also has our open source machine learning framework called Rapids in there. So Rapids is really, you know, a lot of GPU accelerated libraries and components for more traditional kind of machine learning. So, you know, tabular data, but also some interesting sort of newer things like sort of graph analytics as well. And I'm going to show you how you can combine some of these technologies together. So one of the challenges that we have with pathology is just the size of these whole slide images and how amenable they are to all this technology, because just getting them on the GPU efficiently can be a challenge. So to illustrate this, I'm using a few different tools which I'll mention. So first of all, I'm using something called Dusk, which is a really nice library or set of libraries for efficiently scheduling tasks. So you can use, if you take a piece of Python code, normally it will execute serially. So it will execute, you know, on one CPU thread. And to do anything else can be quite complicated. Dust does a really good job of kind of automating some of that for you. And also it doesn't just do it for CPU, it can also do it for any GPUs you happen to have as well. And this is quite a useful technique when we're dealing with whole slide images, because what I've got here is an image from the Chameleon data set. So this is a open challenge for pathology, part of the MICI. There's a MICI challenge that ran a few years ago. And I'm going to load one of these images, and as we always do in pathology, because just the size of them, you know, cut it up into different patches and then do some pre-processing. So typically just sort of threshold it. So what I've done is I've already just imported some libraries, fairly common libraries that you might use for this sort of thing. So these are all sort of, you know, either part of the Rapids ecosystem or just sort of generic, you know, data science kind of tools that you would often see. And I've already created this local cluster. So this is using Dask. This is a Dask cluster. And you can see here, I have told it to use processes. So what this will actually do is, for the code that I launch, it will actually execute a completely separate Python process. And what that will do is bypass some of the locking that Python does automatically, the GIL, as some of you will have heard, global interpreter lock, because that can really throttle performance. It really depends on the sort of things you're doing. If you're using something like NumPy, it doesn't matter, because NumPy kind of takes care of the threading for you. But if it's just your own code, you may, and particularly if you're working with sort of external resources, you may find that you need to use something like this. So I'm also using a new tool that has recently been added to Rapid, which is called cuSim. So the Q sort of typically denotes this is a CUDA, you know, a GPU accelerated component. And I'm using it for fast image loading. So you can see if I load, this is just a thumbnail of this whole slide image, but you can see I've loaded this whole slide image using cuSim. And what you may notice is just the size of it. So if you're not just loading a thumbnail, then the true size of this is about 90,000 pixels by 127,000 pixels. So it's, you know, it's pretty big. And most of it, of course, is actually just sort of blank. There's not a lot in there. This is a kind of composite image, obviously made from a few different slides. And even the bits that are the slides are mostly just glass and not a lot of stain. So, so the first thing that we do to conserve any kind of resources to try and threshold this. Now, if you do this serially, it will take a really long time to do. So what I've done is create a really simple function which does the thresholding. It just looks at the variance of the data within a particular, you know, area that I pass it. And I'm not going to describe what this code does, but essentially just loops through the patches and then in parallel kind of processes them. And if I run just to declare these functions, nothing will happen at this point. But if I run this piece, this is now going to run through that whole slide image and threshold everything. And the output from this will be a long list of tiles, 64 by 64 tiles that we can use for some sort of analysis. So I'm gonna run this now, and you can see that there's a bit of activity going on in the displays on the right. Now these are showing me, these are some really nice user interface tools that are part of this sort of Dusk infrastructure. So what it's done is built this graph out of my code, and wherever it can parallelize that graph, it has done so. And you can see the process, the state of each kind of process that's running. Basically, each one of these is a chunk of that input image that it's processed. And then at the end of it, when it's completed, which it pretty much has now, it will then compile those results, because of course, we've got separate processes and threads that have been independently processing this. So at the end of it, we need to collate all that data into a list that we can use. And there we go. So it's finished running. We've got 389,000 tiles that were above the threshold. So these are 64 by 64 tiles. And it's done that in less than a minute, which may seem like it's quite a long time, but this can take a seriously long time if you try and do it just using kind of traditional techniques. Now, what I've done is I've downloaded a kind of off-the-shelf variational autoencoder. And so each of the little tiles that we've thresholded, I've actually pre-trained this so that what this variational autoencoder does, it learns it learns some embeddings. So it learns the fundamental kind of underlying data that best describes and most concisely describes each one of these tiles. So the most kind of discriminant features, if you like. And the way it does that is by learning how to recreate it from just a few small variables. Like I said, this is a well-known piece of code. It's not, you can fairly easily download something similar to this and run it yourself. I'm going to show you what a couple of the tiles that are going to be loading look like. So you can see these are 64 by 64 tiles. And if I actually run them through this variational autoencoder, the pre-trained one, you can see what's actually going on. So every other cell here at the bottom is the input and then the output. And you can see the output, it's like a sort of fuzzy version of the input. But what it's doing is it's kind of capturing the key kind of elements of that image. And that shows us that it's actually learned something meaningful. So what you could do at this point is then say, well, what can we learn about this whole slide image? Can we, to make the problem a bit more tractable, why don't we, rather than ingesting, the actual image data, why don't we just ingest the latent, the embeddings that our variational autoencoder has learned, and then see if we can do some analytics on that to, maybe reveal something interesting. So what I already did was I saved all these, the data from each one of these 390,000 tiles, and I'm going to run a separate notebook now, which actually is using some of the Rapids tooling, and I'll describe what's going on here. So I saved it as a data frame, and I'm just going to load that data frame, and then it will just give us it's just going to show the first couple of elements in rows inside this, and you can see we've got these latent var 0, latent var 1, all the way down to latent var 31, and then we've got an X and a Y. So the X and the Y are actually telling us the coordinates within the whole slide image of the tile. And then the latent var, these are the embeddings that have been learnt by the variational autoencoder. So we've got one set of these for every tile. So, can we do something kind of meaningful with this data? So the first thing you can do with these data frames that are used in data science a lot is just do descriptive statistics. And in this particular case, we're not going to get anything particularly meaningful from it. You can also do things like principal component analysis. So this is obviously a very common operation that you might want to do. So again, this is really perhaps showing us the even more meaningful sort of subset of that data, reduced to 3 components. And we can do some nice and visualization of this. So one thing we can do is perhaps produce some sort of heat map that shows the correlation between each of our embedded values that we've generated. So if I run this, what you'll see is it's like a sort of kind of confusion matrix that shows us for each one of our latent variables, how do they positively or negatively correlate with all the other features. So you can see some features do and some don't, and you can see you've got the X and the Y there at the bottom, and our embeddings for the rest. So that can be a really nice visualization. We can also do things like produce kind of a scatter plot for our principal components. So now this is actually running on all 390,000 data points, but we can produce quite a nice kind of scatter plot. Obviously, there's nothing particularly meaningful in this case. The scientific value is close to 0, but I'm hoping you can see the potential for some of these tools. And you can do other types of plots as well. I won't dwell on this. But what I wanted to show you was how we could actually turn this data into some sort of graph. So what we can do is we can use a nearest neighbor feature in the Q neural network library. And we can find all the nearest networks in this 32-dimensional sort of latent feature space for every single tile. So I'm just going to run that. That is actually, so for every, you can see there's some GPU utilization as it does this. And what it's done, it's found the nearest neighbors for every single one of our 390,000 tiles, nearest in the feature space. That is great. So we've got these, we've got the 5 nearest neighbors. If we want to do something, that you can see that ran pretty quickly. If you want to run this again, not on the GPU, it'll take a seriously long time. Tens of minutes to run. This is very much the idea of this Rapids toolkit, is to make these sort of data analytics almost real time, even on very large data sets. So I'm just printing out here. This is basically showing us a new data frame that we've generated that for every node, it's telling us the distance between every other node. And you can see we've got 390,000 rows. To turn this into a graph, we need to reformulate this in a format of basically the connections between all our nodes, so the edges. So we need to generate an edge list, and that's going to have a source node, a target node, and then optionally a weight between them. And the weight is going to be this sort of distance that we calculated. So if I run that now, there we go, we've reformatted. We've now got 1.5 million edges, and we can turn that into a graph. Again, this takes a few milliseconds to run to turn that into a graph. And once you've got that graph, then of course we can do there's all sorts of standard graph analytics algorithms that you can run, things like number of triangles, core numbers. But the cool thing I'm going to show is how to actually turn that into, how can we visualize that graph? It may seem like an insane thing to do for 1.5 million edges, but you can actually do it in almost real time. So I'm going to run this Force Atlas layout. You can see it's using my 2 GPUs quite heavily for a couple of seconds. And that is basically used a sort of physics simulation, treating each connection between each node as a spring. And it's trying to find the sort of lowest energy state. And once you've got that, so we've basically got an X and a Y coordinate. These are layout coordinates. So now we can just actually run a visualization on that. And there we go. That is actually a visualization of every single node in this graph and all the connections between them. And like I say, scientifically, there's nothing particularly interesting in that. It's mostly noise. But if you have a real problem to apply to this technology, then this could be really useful. So I see we're pretty much nearly out of time. Perhaps want to leave a few minutes for any questions that come up. If none come up, I can maybe show a little bit more. I don't know if anybody's monitoring the chat.
Yeah, no, sorry.
Sorry, Kathy, you go on. I was just going to say nothing in the chat.
Nothing in the chat, yeah.
There's quite a lot to take in there, I appreciate. But like I say, if you have a look at the Rapids toolkit, if anybody's interested in that, it's open source, you can download it. All the containers I'm using as well are based on containers from NVIDIA's NGC container repository, so you can download all that as well. The other thing I was going to show very briefly was this DALI notebook. So I don't think I've really got time to show it, but DALI is a GPU accelerated image augmentation library, and that can be really useful if you're doing some intense sort of perhaps image pre-processing for deep learning. If you're finding that your CPU is really holding up the sort of deep learning process, then you can offload some of the augmentations to DALI to do some of that for you. And it's quite a powerful feature. It can chain these things together and do all sorts of transformations. So it's perhaps worth a look into.
And I suppose just to tie up with what I was saying about the data transfer bottlenecks before, I mean, the whole thrust of what is happening with DALI and Rapids is that we're trying to get to a point where DALI can load the director straight into the GPU memory, and then Rapids can do an awful lot, as Johnny just showed, with the data while it's on the GPU. So this is trying to make the whole pipeline sort of super, super efficient and open up the world of advanced processing with really big data sets like computational pathology. Thanks, Johnny. That was brilliant.
No problem.
Yeah, thank you very much, both of you. That was a tour de force. So I guess if anyone who's joined has any more in-depth questions, they can just reach out to you, and I guess
yeah, absolutely. My email is in the chat, so feel very free to drop me a line. And there was a whole bunch of stuff we didn't cover about containerizing your applications and how that works. So if people have questions about that, we've got resources I can forward the links to.
Hey, fabulous. Thank you very much. That was great. And thanks to all the other speakers who joined. And we had a really fruitful conversation, and I hope that some of you will follow up, and we can see a lot more collaboration between the academics and the private sector. So yeah, thanks again for taking the time today, and we will make all the material available on our YouTube channel. And Rob, Johnny, if you have any material to share, we can upload that in our shared drive and disseminate it to the attendees as well.
Brilliant. Thanks, Kathy. Can I sneak in one quick announcement? Would that be okay? That there's an event on the 7th of July. We're announcing the go live of what is going to be the UK's most powerful supercomputer that's going to be dedicated to health and life science research. A lot of the big workloads that are going on there earlier bioimaging, so it might be interesting to people. And it is free. We're not putting out an open call yet, but it is free for the people in the bioimaging community, in the biomedical community to use. But we're not calling for applications right now. That may well come, but just to give you a sense of how it's operating, I've put the link in the chat, so please do attend. Just had to sneak that in there, Kathy.
That's fine. That's fine. Perfectly fine. Excellent. Thank you very much. Yeah, so thanks everyone who attended the webinar today, and I hope we'll see you in the future. And Rob and Johnny, thanks for the demonstration. That was great. And I hope we can follow up in the future as well. So yeah, then I hope you all have a lovely rest of the day, afternoon, morning, wherever you're based. And yeah, I hope I see you in the future in one of our events. Bye.